chemistry and regular chemistry, and we talk about hydrogen ion solutions. We don't talk about hydronium ions. It's a little confusing for me sometimes. So water automatically contains some hydronium ion and some hydroxide ion, because water molecules can act as both an acid and a base, and when they bump into one another, sometimes hydrogen ions get transferred. Now, it doesn't happen very often. The concentration of hydronium ion in pure water is 1 times 10 to the negative 7 moles per liter. And, not surprisingly, the concentration of hydroxide ion is also 1 times 10 to the negative 7 moles per liter, because when two of these bump into one another and exchange a hydrogen ion, you get one of each of these, don't you? Yeah? So the concentration of those ions are equal, and they're very small. 10 to the negative 7 moles per liter is 0.00000001 moles per liter. That's not very much. 1/10,000,000th of a mole of hydronium ions per liter of pure water. However, this reaction is reversible. Hydronium ions and hydroxide ions can also bump into one another, and the hydroxide can steal that hydrogen ion back. It's why we don't get very many of these, because we end up with a balance, also known as dynamic equilibrium, when we have very, very small concentrations of these. But here's the important part. If I were to add more of these, and how would I add more of these that were there already? What would I add to the water to increase the concentration of hydroxide ion?
Sodium hydroxide.
Sodium hydroxide, potassium hydroxide, lithium hydroxide, calcium hydroxide. Something that contained hydroxide ions. Yeah? If I dissolved one of these compounds in water, wouldn't the concentration of these increase? And because the concentration of these increases, wouldn't these things bump into one another more often? And that would make these decrease. Now, for reasons that we'll talk about later on, that have to do with this dynamic state of equilibrium, the concentrations of these two are inversely proportional. If one goes up, the other goes down. Yeah? Now I'm going to go back and quickly explain again why that's the case, but it's not important in this particular chapter that you understand why that's the case. Okay? We'll get into the equilibrium aspects, something called the Chatelier's principle, stuff like that, in preparation for the STAR exam here after break. But for right now, for the purposes of chapter 15 and 16, it's not important that you understand why the concentrations of hydroxide and hydronium are inversely proportional. One goes up, the other goes down. But I'll explain it to you real quick again, because it might help you. So these are produced when water molecules bump into one another and occasionally transfer hydrogen ions. And of course, these things can bump into one another and go back and form water molecules, can't they? Right? Now the question is, how often do these things run into one another? Because their concentrations are very low, they don't run into one another very often. But if I increase the amount of hydroxide ion by adding a source of hydroxide from some other place, a compound that contains hydroxide ion, if I increase the concentration of these ions, don't they bump into one another more often? And if they do that, isn't this reaction going to occur, the backwards reaction, going to occur more often, and doesn't that use up these things? So if I increase these things, I end up using up these things. And the opposite is true as well. If I create more hydronium ions, how might I create hydronium ions? Ooh, take one of our really strong acids, such as HCl, dissolve it in some water, yeah? Strong acids give up their hydrogen ions very readily, so almost every molecule I dissolve, as we talked about the other day, of HCl, gives a hydronium ion. So I could increase the hydronium ion concentration by dissolving some HCl in water, yeah? And if I do that, these things are going to run into one another more often, and the concentration of hydroxide is going to go down.
But wouldn't the concentrations of whatever you have to add, wouldn't they also go down?
Yeah, but we're talking about
Yeah, but
this
you're
being
adding
a
some.
10 millionth of a mole, and this being maybe a tenth of a mole. And if I put a tenth of a mole per liter of hydronium ions in there, and I lose, what's the most I can lose? If all the hydroxide reacted, I'd only lose a 10 millionth of a mole, and this would go down to 0.0999999. Okay? So as I add one, the other goes down. Okay? Now, how do we express inversely proportional relationships? I'll remind you, when we did it with pressure and volume, we said pressure times volume equals a constant. Oops. Pressure times volume equals a constant, yeah? That was a way we had, mathematically, of expressing an inverse proportionality. Because if volume increases, pressure would have to decrease if their product stayed constant, yes? Well, the equivalent here looks like this. Some new notation in chemistry, not in algebra, but in chemistry. Square brackets around something means the concentration of that something in moles per liter. So when I write this, what does that mean? The molarity of chloride ions, doesn't it? If I write this, what does that mean? The molarity of hydroxide ion. If I write this, it means the molarity of hydronium ions. We okay? So it's the notation that we use in chemistry, square brackets. So that means that the concentration of the hydronium ion multiplied by the concentration of the hydroxide ion is always 10 to the negative 14. So if one increases, the other decreases, right? Because that's a constant. We okay? How we doing? Now, pH, that's equal to this.
Yay!
Isn't it a log base 10 anyway, so you don't need to have the base 10 there?
Just reminding you that we're doing base 10 logs instead of some other base. How many of you have never done logs before? You've all done logarithms before. Good. And the things that you've done with logarithms, far more complicated than what we're doing here. What does this mean? It means you take the molarity of hydronium ions, plug it into your calculator, hit the log key, and then change the sign. Can you take the log of a number and change the sign? I know that's two things that you have to be able to do, but I'll bet you can do it, huh? Now, it gets a little worse than that. We need to be able to go backwards from that. We need to be able to take the pH and find out what the molarity of the hydronium ion is. Can you take the pH, change the sign, and take the inverse log? So if you groaned when you saw the log thing up there, that's all we're doing with logarithms. Are we okay? Are we going to make it? Going to survive?
Maybe.
Okay?
not going to deal with log or anything other than n.
Log of the, you're gonna deal with the logarithm of the hydro.